Uh, okay, this may be the actually the last meeting of our Foundations of Probability seminar this semester. We'll be starting again in the fall, and if you want to be on the mailing list, and you aren't, I know there's some people here that got the news from Anand or from Francesco. And if you want to be on the mailing list of our seminar, please let me know, Glenn Schaefer at Rutgers Business School. Um, uh, so this is probably our last meeting of the semester, and we have the honor to have Francesco Orabona talk about, well, there's, you see his title, Tight Concentrations and Confidence Sequences from the Regret of Universal Portfolio. So what is this? It's a connection between machine learning and information information theory. Francesco was explaining to me that Thomas Cover is the one that brought betting into information theory, and as a consequence of his work, people in information theory are accustomed to a betting vocabulary, but it's somewhat different from the game theoretic probability that I've been so interested in recent years. But I'm certainly interested to hear about it. So I'm going to turn the floor over to Francesco.
Okay.
And since I'm the only other person in the room, you can take your mask off if you like.
Sounds good. Sure. Okay, so thanks, Glenn. Thanks for inviting me. Give me the possibility to tell you something about my work. So this is a brief outline of the talk in basically 3 parts. I will tell you something about betting on a coin, what is this problem, and especially from an information theory point of view. And then I'll tell you how you can use these algorithms to bet on a coin to derive concentration inequalities, and also the same algorithms to do optimization. So let's start with the first part, betting on a coin. Okay, so what is this thing? This is a very simple game. You start with $1, and in each round, you bet on coin outcomes that are CT, are numbers -1 or +1, and you bet X of T money. So you're basically betting that you will observe a head or a tail. And the money that you bet, they will have the side of the coin encoded inside here in the sign, so that if we bet positive money, we say that you're betting on observing a +1. If you bet negative money, you're betting on observing a -1. Okay. And so the wealth at each time is updated as the wealth that you had before, plus the multiplication of the outcome of the coin multiplied by how much money you bet, so that if they have the same sign, you're winning money. If they have different sign, you're losing money. Now, there is only one rule: you cannot borrow money. And so the moment that you lost of your money, the game is over. And what is your aim? The aim is that you want to maximize the amount of money that you make on all the sequences where the sum of the coin outcomes is different than 0. Okay, because basically, if the coin is fair, there is nothing that you can do. You cannot really win money out of this game. But if one side is appearing more often than the other, you want to take advantage of these and win as much money as possible. Now, Schaefer and Wolf started in 2001 this line of research that tried to found probabilities on a game theoretic ground through betting schemes. And the basic idea is that you can define almost sure events as the one where there exists a betting strategy that guarantees no negative wealth and diverges to infinity if the event does not happen. And they basically wrote an entire book on this thing. And there are also connection between game theoretic and measured theoretic results. But at the same time, in the book, there are no finite time concentrations at least in the sense that people in machine learning like to see. And the first game theoretic concentration is actually from 2007. This is a secondary report from Bob that basically derived of the inequality, game theoretic of the inequality. And so they already saw that there is basically a relationship between betting and concentrations, at least in a certain sense. And there is also another part they have a work that is not so widely known, unfortunately. That is this idea of defensive forecasting that basically says that you can do online linear regression through betting algorithms. But it's very specific to linear regression with square laws. You can basically generalize a little bit laws, but it's still everything has to be linear. So this is what basically people did in this field. Now, let me show some kind of a different point of view, that is the point of view from information theory. So let's assume that the coin outcomes are IID. And now the question is how to bet optimally. What is the optimal strategy to make as much money as possible? And Kelly in 56 proposed this idea that if you bet a fraction of your money that is equal to the expected value of the coins, so for example, if the coin is equal to 1 with the probability 0.51, you should bet 2% of your money on observing a 1 on each round, blindly. It doesn't matter if you win or lose, you keep doing this. And he proved that if you use this approach, the expected log wealth, it's linear in time. Okay, so roughly speaking, you can imagine that you can see that your wealth is increasing exponentially in time. Now, what are the key ideas in this paper? The key idea is that he said trying to maximize the expected wealth is not a good idea. The thing that you should try to maximize instead is the expected growth. And this is why it's expected log wealth. But he didn't justify the approach. Fortunately, later, it was proved that this approach turns out to be asymptotically optimal. So if you actually care about wealth, maximizing the expected log wealth is still the right thing to do. But there is a more important bit in this paper that people typically forget, and the fact that he was the first one to observe that gambling and prediction with log loss are completely equivalent. If you care about making money out of this coin, or if you care about doing prediction with log loss on a stream of bits 0, 1, these are exactly the same thing, like exactly. And so you can take any result from one field and use it as it is on the other field. So this means that now we can look at what information theory people did between 81 and 95. And most of their results, they are not stated in terms of betting.
Hey, Mike,
and
Harry Crane.
Okay. They are not stated in terms of betting and in terms of gambling, but they are stated in terms of prediction with the log loss, in terms of coding. But again, the two things are completely equivalent. They map one to one. And so in particular, Cover in 74 defines what I found to be the first, even if I'm not sure this is the first, but this is the oldest paper that I could find, about using a mixture gambling strategy. And I will define later what is this idea. In 87, we already have that people solved completely in a minimax way what is the optimal strategy that you should use if you know that the game will end at a certain time horizon, capital T. But unfortunately, this strategy is computationally expensive. And so people started to study uncountable mixture of predictors, uncountable mixture of gamblers. This is the same thing because, again, they're exactly the same thing. That gives you a closed form. And one of them is this idea of the Krzyzewski-Trofimov estimator, that is this formula here. In each round, you count the number of heads in the past, you add 1/2 divided by number of rounds plus 1. And in 95, people proved a finite time guarantee for the Krzyzewski-Trofimov. So what are the key messages here? By 95, optimal coin betting in the stochastic case was basically solved. We know everything. We know what was the optimal algorithm for finite time. We knew that if you don't know in advance what is the time, you can just use Krzyzewski-Trofimov. Everything will be optimal up to constants. And so that's it. What is the caveat? The caveat is that this entire work here was done in the stochastic case. So you're still assuming that the bits are coming from a Bernoulli, basically. However, in 96, Freund wrote this paper in which he asked at the beginning this very question. It basically says, how do we know that a data source is actually random? it's basically impossible to verify that this is true. So why we should assume it? So he said, instead of assuming it, we should find an assumption that is weaker, but at the same time capture the case in which the coin is actually random. And so he said, the assumption that we study in this paper is that there exists a fixed model whose total loss on the sequence is not trivial. Okay. And why a fixed model? Because in the stochastic case, betting a fixed fraction of your money is optimal in all the possible sense.
What do you mean by non-trivial?
Non-trivial in the sense that the amount of money that the fixed model is making, it's not, it's growing, it's not constant. So if the coin is fair, if the number of head and tails is the same, there is nothing to do. And so, there is nothing to do in that case. So I find this interesting because you can see that it's not trying to define probability, it's not trying to define randomness. It's just saying, at the end of the day, I don't even care if the coin is stochastic or not. What I care is that I want to make money, right? And so I just define a different objective. And the objective is the log wealth of the best fixed strategy V star minus the log wealth of the algorithm. Can I make this difference as small as possible? This is the question. And he proved that Krzyzewski-Trofimov, the same one that was designed to work in the stochastic case, also works for any arbitrary sequence of outcomes. And later, people in information theory, after these results of your Freund, started considering both the stochastic and adversarial setting. So you will find paper in information theory in which they say, in the stochastic setting, this is the result. By the way, the same results will also in the adversarial setting up to constants. So now let me go back to the Krzyzewski-Trofimov. Let me explain a little bit better what this algorithm is doing. So let's say that I bet a fraction of money beta in each round. Okay, at the end of the game, I will have some wealth that depends on this beta. How do I know what is the beta that I should use? Okay, now from now on, there is no stochasticity. This is just a sequence of outcomes, and I just want to make as much money as possible. In order to know what is the best beta, I should know in advance how many heads and how many tails there are in the entire sequence. But I don't know that. And so what I can do is the following. I can take my initial money and I can divide in a bunch of alternative strategies. So I can bet alpha, a fraction alpha of my money with beta 1, and a fraction 1 minus alpha with beta 2. And this will give me a wealth that is alpha times the wealth of using beta 1 plus 1 minus alpha times the wealth of beta 2. Okay, but why just using 2, dividing just my wealth into 2 strategies? I can divide this wealth into a countable number of strategies. And this is exactly what Cover proposed in 1974, and this is exactly the same approach that you will find in the examples in the book of Schiffer and Bob. And what's the intuition? The intuition is that this approach works because among one of these betas that you're trying, one of them will work very well, one of them will make an exponential amount of money, and you don't pay that much for the fact that you are dividing your wealth because the amount of money that you're making is exponential. However, this approach works, but it's something that you don't want to use. You don't want to use it because, computationally speaking, this is not something that you can actually run. A countable approach means that you never have a closed formula. And so Krzyzewski-Trofimov is exactly this idea, but on an uncountable number of possible bets. And so you can show that beta t now comes out of this formula, where this is basically the expectation of the beta times the wealth with respect to this mu, that it's basically the way in which you divide your initial wealth among all the possible beta fractions. And why this is good, why people like that? Because this has a closed form. It's sort of, somehow you got lucky that when you put here this specific distribution that is a shift beta 1/2, 1/2, you get a closed formula, and now you can actually use it. You can actually implement this algorithm. Now, I want to stress the fact that some people might say, is this a Bayesian strategy? Is this mu the prior that I have? Or is this related to the method of mixture by Robbins? And in both cases, the answer is no, because there is nothing random here. It cannot be Bayesian, it cannot be the method of mixture. These are not martingales because there is nothing random here. Everything is an arbitrary sequence of outcomes. So this is the proper way to look at this is just that it's a mixture of an uncountable number of fixed bets that you do. Okay, so this is what you bet with Krzyzewski-Trofimov. What we can show, why people like it so much, we can show that the wealth of Krzyzewski-Trofimov at the end of a game of T rounds is equal to the amount of money that the best constant fraction would make divided by roughly 2 times square root of capital T. So this factor here is exactly the penalty that you pay for not knowing in advance how many heads and how many tails there are in the entire sequence. And you can show, by the way, that the square root of T is optimal. The only thing that is slightly suboptimal is the constant. And you can lower bound this by this quantity here. And you can see that if the sum of the CT is not equal to 0, so there is one side that is appearing more often than the others, this quantity here inside the exponential is proportional to time. And so the amount of money that you make is exponential in time divided by 2 times square root of T. Okay. And this result, this exact formula here, subsume, for example, most of the statement in the chapter T3 of the book of Schaefer and Bob, because you just need that every time this thing is not 0, the wealth will go to infinity. That is exactly what you do. Now, this is optimal only in the case that the coin is actually a coin. If the coin is continuous, what I call a continuous coin, so basically the outcome now is just a real number between -1 and 1, you can still use this approach. This guarantee is still correct. Everything is still exactly the same, but it's not optimal anymore. You can do better. What is the better thing that you can do? You can use universal portfolio from Cover. Universal portfolio is optimal up to constant again, but the annoying thing is that the computational complexity is proportional to T in each time step. We proposed suboptimal algorithms that have a closed form solution in each step, but they're just suboptimal. We know that they are suboptimal, but we design them in order to have something that, again, you can implement easily on a computer. So now let me summarize basically the first part. The first part basically says, if you have an arbitrary sequence of coin outcomes, even continuous coins, so just a number between -1 and 1, and you want to bet on these things and you want to make a lot of money, this problem is easy. It's easy in the sense that without assuming anything and without knowing anything, you gain almost as much money as the best constant fraction strategy. And the best constant fraction strategy is the optimal thing if the coin was actually random. Okay, any question till the, I don't know if, I mean, there are 2 people here.
You have 30 there.
Right.
I had imagined that we would have a camera where we could see 30 people with little boxes like usual. Maybe, I don't know if we don't have a.
I mean, I cannot see the chat.
There's 3 people.
Right, I cannot see the chat.
If everybody had their cameras on, we could see everybody that wanted to ask a question and so on, but we were kind of looking at a blank screen.
Francesco,
Yes.
I have a question.
Yes.
Just to make sure I understand, when you compare it to the best constant fraction strategy, is it possible that the best constant fraction strategy could actually lose money overall? Is that possible?
No.
So
No.
it's guaranteed. It's guaranteed to at least break even. Is that right?
Exactly. Yes.
I see. Got it. Okay. Thank you.
Okay. If there are no other questions, I can go on. I mean, I can get question at the end anyway, but I want to be sure that everything was clear until now. Okay. So let's move on. Now, let me show you what's the connection between betting and concentrations. Suppose that you have a stream of random variables in 0, 1, okay? And let's assume that the expectation condition on the past of all of them, it's mu. Now, this is true if there are IID, but this is slightly bigger. And we want to estimate this mu, and we want to give a confidence interval that holds with high probability uniformly over time. Okay, so in statistics, it seems that people call these things confidence sequences. In machine learning, we just say that the concentration is uniform over time. And so basically, we want to output a sequence of intervals, A, T, B, T, such that the probability that the true expectation is in interval for all the time steps is greater than 1 or minus delta. Okay, and I mean, of course, we would like the width of this confidence interval to shrink over time, and possibly as 1 over square root of t, because otherwise the problem is stupid if we don't put this constraint. Now, how do we estimate? We can just estimate the true mean by the empirical mean. And then we could use a concentration inequality that holds uniformly over time to construct a confidence interval, right? This is a sort of classic approach. These are even bounded random variables, so there is really nothing to do here. Everything is known. So we say that the true expectation is plus or minus the empirical mean, and this plus or minus quantity will be 1 over square root of t, and will depend on the probability of failure delta, and it will depend on the variance. K in K here, I'm putting basically the dependency on the variance of the random variables. So for example, if you use the concentration by Maurer and Pontil plus the union bound, you get exactly this kind of result. Now, what is the annoying thing? The annoying thing is that when the number of samples is small, where small, I cannot quantify small, it will depend on the variance and it will depend on the random variable. But if you don't have enough samples, you might end up with something that says the true mean is something like 0.3 plus or minus 3.7. And remember that these were random variable between 0 and 1, so this is completely useless, right? So ideally, we would like the confidence intervals that we get to be never vacuous, possibly even with a single sample. Now, what is our approach to this problem? We derive concentration inequalities from coin betting algorithms immediately. Basically, it's incredibly simple. So what is the key idea? The key idea is the following. There are two facts. The first one is that a concentration inequality basically says that the empirical average cannot be too far from the true expectation. And another one is Will inequality that says that you cannot gain money betting fraction of your wealth on a fair coin if you're guaranteeing that the wealth will never be, that will always be non-negative. Okay, so the probability that the maximum of your wealth is bigger than 1 over delta is less than delta. Okay. Now you can basically relate these two facts one to the other, and you get immediately the concentration. So how you do that? You say, I start with $1, and I use a betting algorithm to bet on the outcome of the xi minus mu. Okay. The expectation of this thing is 0. So this means that when I bet money on this thing, I can apply the Will inequality. But not only that, let's say that I use a specific betting algorithm. Let's say that I use Krzyzewski-Trofimov. Krzyzewski-Trofimov tells me that my wealth is at least this quantity, because this is exactly what it guarantees me. It doesn't even matter if these outcomes are stochastic or random or not. This is always true deterministically. So the wealth is a martingale. I use Will inequality, and I lower bound the wealth of the algorithm with the guarantee that I have. And immediately I get the concentration. That's it. The probability that the maximum of this quantity is bigger than 1 over delta is less than delta. If I simplify, I get a usual concentration, 1 over square root of t type. I will pay a logarithmic factor in time to have the time uniformity. Okay. So this is nice, but it's sort of nothing new. I mean, the concentration that I got is not even optimal in a certain sense. But let me tell you some interesting things. So let me tell you how can we build on this. First, it seems that we first noticed this connection in 2019, but actually we noticed before, we noticed in 2017, and I actually shared this result around. And why in 2017? Because in 2017, there is a particular result that came out. And it's this result by Racklin and Sheridan. That is exactly 2017. This paper says that concentration and regret guarantees are completely equivalent. Every time you have an algorithm that is able to guarantee you a regret, where by regret, I mean that the difference between the loss of the algorithm minus the loss of the best is bounded, you can build a concentration, always. It doesn't have to be a betting algorithm. This is always true. And by the way, it also goes in the other sense. Every time you have a concentration, from the concentration, you can derive an online learning algorithm. So why this is true? This is true because some martingale inequalities here are basically deterministic in nature. And in online learning, we basically prove deterministic inequalities. This is what we do. And the key idea in the paper was not just the fact that you can observe that that these two things are equivalent, but the fact that you can derive new results in one field using known methods from the other field. However, in this paper, there was.
What are we talking about here? What field?
Online learning and concentrations. You can derive new concentration every time you have an online learning algorithm with a regret guarantee.
So regret guarantees are on which is which?
Regret are online learning.
And what is concentration?
Well, call it whatever you like. Probability, statistics, I don't know. Okay. However, in this paper, there is no online betting algorithms. They didn't know about that, or they didn't care. I don't know, actually. And the other thing is that their concentration are not time uniform. So our observation instead is building on that. It's exactly the same vision. It's exactly the same thing. It's saying we want to take a regret from an online learning algorithm, from an online betting algorithm in particular, and we want to see what is the corresponding concentration. And we want to get something new. And I mean, it seems that we couldn't find anything before 2019 of this idea of transforming wealth guarantees of betting algorithm into new concentration. I mean, I had a long discussion with Glenn before about this fact, if this idea is new or not, if it was in this book or not. In the end, I think I can say that Glenn considered this idea trivial, but still, the fact of obtaining new concentration might be mildly interesting, if I interpret it. And so in particular, what we got was that in 2019, we converted a betting algorithm into the law of iterated logarithm for sub-exponential random variable in a Banach space. And this was, I mean, this might seem difficult, but actually the fact that you just have to have a betting algorithm and then the entire thing will go through sort of automatically. But now the next question is that, can we do better than that? What is the optimal betting strategy? Because we know what is the optimal betting strategy. It's universal portfolio. What is the corresponding concentration that we get from universal portfolio? So for universal portfolio, you can show that the expected log wealth for sure will be less than the expected log wealth of the best constant betting strategy, but it's also not too far from it. And this quantity here is actually optimal. So this is what I mean by optimal. This is basically the best thing that you can do in this sense. And so what do we get when we use this optimal betting strategy? So continuous coin betting with the universal portfolio is just universal portfolio with two stocks. We immediately plug the regret of universal portfolio into Ville inequality, and we get this thing that, as far as I know, it's new. It's a new concentration. It's also particularly weird. It's not stated in the usual way. It's stated as the maximum over time of the maximum over beta that depends on the unknown expectation of the random variables, of some quantity here that depends on the random variables and the unknown beta, mu again. And then there is RT, that is the regret of universal portfolio, that in the worst case is this 1/2 log t. Now, we can prove that the set of mu that guarantees that this is true, the inverse of this is true, is an interval. And so you can invert this thing numerically with binary search, and you can get an actual confidence interval on mu. So what is the key message here is that the optimal betting schemes are known. We can just use them and we can see what we get. And it turns out that we get some concentration that are new. And the other important thing is that we never have to run the algorithm. We don't actually run universal portfolio because running universal portfolio is particularly annoying. We don't have to run it. The only thing that we need in this entire thing, this can be evaluated, and this does not depend on the algorithm. The only thing that depends on the algorithm is the regret. But I don't have to run the algorithm to know the regret. I already know what is the regret. So I never run the algorithm, and I immediately get my confidence sequence. And so I also avoid the fact of having to run this algorithm. So let me show you some numerical results of these. We did experiments with 4 different random variables. The probability of failure here is 0.05. And we compared with the algorithms in Dubai Smith, I'm sorry if I mispronounce it, and Ramdas. And basically, the approach is very similar, but the difference is that they, instead of using universal portfolio or instead of using any known betting strategy, they say we can design any betting strategy. And in particular, we can even come up with heuristics that don't have any guarantee, because anything you plug in Will inequality, as far as the wealth is non-negative, will give you a concentration anyway. And so most of the things that they propose are of this sort, and there is a final one that is a finite mixture of gamblers that seems to have a very high computational complexity, because you basically have to run a bunch of different gambling algorithms for each different fraction that you try. So these are the results. This is the Bernoulli 01. The red line is the one that we get from our algorithm. So these are the confidence sets. This is the upper confidence, and this is the lower one. And the true mean is here is 0.1. So you can see that all the algorithms are converging to 0.1. And I compared, basically, the red one is our algorithm. I compared to 2 different algorithms from the paper that I just mentioned, and a paper, this is our 2021, that is a classic law of iterated logarithm concentration inequalities, just in a closed form. Now, what is, and this figure here is just the confidence width, so it's just the difference between upper and lower bound. What are the interesting things to observe? First, when the number of samples is large enough, it doesn't really matter what you use. They're all equal. They're all equally good in a certain sense. But the important thing is that when the number of samples is small, our strategy dominates the other. Now, what's the reason for it? It's only the fact that we are using a betting strategy that is optimal. That's it. And in particular, when you have few samples, designing a betting strategy that is good on few samples, it's very, very difficult. It's extremely difficult. But if you just have the optimal strategy, you cannot really beat that thing with few samples, like 10, 20 samples. It's basically impossible to beat the optimal strategy. And the results are similar in all the other settings. This is a Bernoulli 05, beta 11, and a beta 1030. And the other thing that I want you to notice is that our algorithm, it's the only one that with one sample will give you a confidence width that is strictly less than 1. And we can actually prove it mathematically that this is true. It doesn't matter what is the random variable. The confidence width that you get, it's always strictly less than 1. And this is exactly the property that we want. And again, it depends on the fact that the algorithm is optimal. It has a guarantee, and so we know exactly how it will behave. Okay. I guess I can ask for questions here too. Okay, no questions.
I'll bite. I have
Yes.
one question. So you're saying, okay, so for any betting algorithm, you get a concentration inequality, but are there situations where you can prove a tighter concentration inequality than betting, because it doesn't correspond to a betting algorithm? There's no betting algorithm that would yield this concentration inequality.
This is a question that you should ask to Aditya, probably.
Well, he's here, so I could just ask him.
So it turns out that so for confidence sequences, the use of martingales is provably admissible. So I think optimality is actually really hard, because what it turns out that confidence sequences that are looser early on are tighter later on. Things that are tighter early on are looser later on, and there's this inherent trade-off. So like log boundaries will be tight at later times, but they must be loose early, and so on. So optimality is actually very subtle to talk about, but you can talk about admissibility. Admissible, you call a confidence sequence admissible if you can strictly dominate it at all times. And it's otherwise two things are incomparable. It's tighter at some time, looser at some other time. So it turns out that admissible confidence sequences must be based on martingales plus Wheel's inequality. This must be the case. If you have a confidence sequence, any confidence sequence, I can take it, I can construct a backward Doombs martingale out of it. I can apply Wheel's inequality. I'll get a new confidence sequence that's either the same as yours or strictly better than yours. And so martingales plus Wheel's is pretty much a universal way to describe it. And a martingale is a betting strategy. A non-negative martingale is a one-to-one mapping to the betting strategy. So this class of algorithms, that we're looking at is essentially the right class. There is no other way, at least for a confidence sequence. Now, for a confidence interval, things could be different. But for a confidence sequence, this is the only class really that we can consider to get admissible bounds.
Thanks.
Thanks.
Just to ask a stupid question, how is admissibility defined in this context?
Oh, you can all still ask Aditya.
Yeah,
yes,
so you say a confidence sequence is inadmissible if it is strictly dominated by some other one at all times. And
the confidence sequence meaning that it's just it's basically a time indexed confidence intervals.
But that's not, yeah, but it's uniformly valid over all time, from 1 to infinity. So it's simultaneously valid over all time. It captures the true mean at stopping. You can say it captures the true mean even at stopping times. So it's a sequence of intervals that are uniformly valid. And so a confidence sequence would be inadmissible if you can find another one that strictly dominates it at all times, and it's admissible otherwise. And so there's many admissible confidence sequences. That's like the simplest thing you could ask for out of a confidence sequence. At least it's admissible, and those must be constructed using martingales and plus Wheels.
I see. So basically, we are looking at the plots that Francesco you showed on the left-hand side for the different simulation. It's just those sequences,
those
and
bands.
then they have to be
Right.
Inadmissibility would just mean that it's strictly wider. On the top, it's higher, and on lower, it's lower.
Right. Yeah.
Right.
Thanks.
Okay.
Just a quick random question. All the examples you're showing here for bounded random variables, is that one of the conditions here? And also, I guess that there is also this whole discussion, but I can ask you and Aditya later. One of this discussion of admissibility and all that, is that for bounded random variables, or is that for particular, or is that just general?
No, admissibility is general for any functional of a distribution for any unbounded. It's like a much more general statement. But yeah, in this talk, I think we're just dealing with bounded random variables.
Right. So the results that I mentioned here, you see these results that I'm saying here. The variable, the result that we proved in 2019, this is actually sub-exponential unbounded random variables in Banach spaces. Okay. This makes the problem a little bit different, because you cannot bet money on things that are unbounded, because you might lose them, all of them, in one round. because you don't know beforehand how much you're gonna win or lose. And so there is no way you can control how much you lose. And so what happens is that the approach that we followed here is to say, okay, the wealth might become negative, and this might be a problem, but the expected wealth, we can construct a strategy whose expected wealth, it's lower bounded by, it's non-negative. And then it's fine. Then you can still use will, then everything goes through and it works. So, I mean, the boundedness here was mostly for to apply universal portfolio, because universal portfolio, it's for bounded stuff. But if you don't care about using universal portfolio, yeah, you can still using the same approach in a slightly different way.
Thanks.
Sure.
So I'll ask a question about your pictures.
Yes.
What's this concept of admissibility? So when you get in larger values, your red line, I don't see the red line so well there, but yeah, I see it. The red line by this, those other lines are also admissible, or are they? Are the other algorithms?
Yeah, they are the same. They are all the same family in a certain sense.
They're all admissible.
Yes.
And loaded in that
Yes.
sense. So, which means there at some point the red line is necessarily not best.
Yeah, but I already know it. So, for example, let's do a practical example. From among all these lines, all of them at a certain point have to be worse than this. What color is this? The outward line.
Yeah.
Because this is the law of iterated logarithm. So sooner or later, that thing will be better for sure. So I mean, there is and this is a discussion that I wrote in the paper, and the fact that what is on where you want to focus. You want to focus on a small simple regime or a large simple regime.
But do you have are there ways of giving a user?
Yes, a user no, but the designer of the betting strategy knows that. I know that. I know how to design a betting strategy that focus on one part or the other. So I can tell you that universal portfolio is focusing on the first symbols. So I can prove that.
But I guess my question was, are there tools that would make it easy for
Not
a
easy.
user to?
Not easy.
Okay. Thank you.
Okay. Okay, let me move to the last part because I don't want to go too much over time. So let's now see how can we use exactly the same idea to do stochastic optimization of convex functions. Okay. So we want to solve this problem. We want to minimize a function. It's a convex function. We only assume that the function is Lipschitz. Okay. And we have access to first order stochastic oracle that gives us stochastic noisy estimate GT of the gradient or subgradient, it doesn't matter, of f in x of t. Okay, so we assume unbiasedness. So in particular, we assume that the conditional expectation of the stochastic gradient, condition on the previous ones, is actually equal to the gradient of f in x of t. Now, what is the simplest algorithm that we can use in this setting is stochastic gradient descent. So in each step, you move in the negative direction of the stochastic gradient and multiply it by what we call learning rate or step size. And it turns out that choosing the correct learning rate is sort of a black art. Why it's so difficult? Let me show you an example. You want to minimize this function, absolute value of x minus 10, and you want basically to arrive here, and you start somewhere, let's say that you start from 0, and every time you evaluate the gradient and you move in the minus direction, so basically you will move like this. And by how much you move by quantity that depends on the learning rate. So if the learning rate is too small, you will never converge because it will take forever to reach the optimum. On the other hand, if the learning rate is too large, you will converge quickly in the area of the optimum, but then again, you don't converge because you cannot be more precise than the step size. So how do we solve these things? it should be obvious from this picture that the optimal learning rate depends on how many iterations you do. The more iterations you do, the smaller you want learning rate to be. And also it should depend on the distance between the initial point and the optimal solution. If you're far from the optimum, you should take large jumps. If you're very close, the jumps should be small. And in fact, this is what we know from the theory. The theory tells us that the optimal learning rate is something like alpha, where alpha is some magic number that we will discuss in a moment, divided by the square root of the number of iterations. If you use this learning rate, the convergence rate is something like 1 over square root of big T multiplied by a constant. This entire thing here, it's a constant with respect to capital T. But this constant is arbitrarily big. What is this constant? This is the optimal point minus the initial point divided by alpha. Again, alpha is the number that you have to choose here, plus alpha times the Lipschitz constant squared. Now, if you look at this thing, you can calculate what is the optimal alpha. And the optimal alpha turns out to be the distance between the optimal solution and the initial one divided by Lipschitz constant. And if you use that as inside your learning rate, you would get this convergence rate that is optimal. It's optimal because there is a lower bound. We know that it's optimal. However, what's the catch? You don't know the optimal solution. You are looking for it. So there is no way you can actually use this thing into an algorithm. So can we do better than this? Can we have an algorithm that doesn't need to tune anything, that's sort of automatic? And by the way, this is exactly similar to not knowing what is the optimal beta in the gambling scheme that I showed you before. It's exactly the same thing. Before there was an optimal beta, you didn't know what was the optimal one. So you used a distribution over all the possible betas. And given that the optimal beta will gain an exponential amount of money, this still worked. We will use exactly the same approach here. So this is the entire slide that explains the entire algorithm. We will do optimization through a betting procedure. And for simplicity, just 1D in this slide, but then we can extend even to Banach spaces. So you can use any betting strategy that you like. The only thing that we have to assume is that it guarantees you some function h money of the sum of the outcomes. Okay, so for example, if you use Krzyzewski-Trofimov, you know that you will gain this exponential amount of money that depends on the sum of the CT. So let's say that you want to minimize this function, absolute value of x minus 10. And we set the betting game in this way. The amount of money that you bet is equal to the point on which you query the gradient. Every time you receive the gradient, minus the gradient is the outcome of your coin. This is exactly a -1 or a minus or a +1 in this case, so it's exactly a coin. So my claim is that the average of your bets will converge to the minimum of the function. And not only that, the rate will depend on how good is your betting strategy. And the proof is so simple that it can be done here in the slide. I will not do it, but this is just basically Jensen inequality, convexity, definition of the function h, then you maximize, and then definition of Fenchel conjugate. That's it. So let me just read the first and last. The function in the average of your bets minus the function in the optimum, you would like this quantity to go to 0. And this is less than the Fenchel conjugate of the function h evaluated in the optimal solution divided by capital T. Okay. And so the Fenchel conjugate has this particularity, this property that if the growth rate of h is large, the growth rate of h star is small. So the more money you make, the faster you will converge. And so we can use Krzyzewski-Trofimov as it is to do optimization. How does it work? Krzyzewski-Trofimov tells you bet this fraction of money of your current wealth. X0 is just the point where you start. It doesn't really matter. You can put it to 0 for simplicity. Now let's use our reduction. The coin are minus gradient. The wealth is the initial dollar and how much money you make in each round. How much money you make in each round is how much money you bet, that is x, and the coin, that is minus gradient. This is the entire algorithm. This is not stochastic gradient descent, but this is as simple as stochastic gradient descent. And you can show that the guarantee, you just have to calculate the differential conjugate of the exponential quantity of Krzyzewski-Trofimov. So it's immediate that this is the guarantee. So this is only one dimension, but you can actually generalize it even to Hilbert spaces easily. And you just have to assume that now the function is Lipschitz. And the only difference is that now these outcomes are vectors, and this becomes an inner product, but the guarantee is exactly the same. And the algorithm is as simple as before. I mean, this entire quantity is a number. And this is basically almost an average of the past gradients, stochastic gradient that you observe. Now, why this guarantee is good? Let me convince you why this guarantee is good. Let me rewrite it in this way. This is exactly the same guarantee. Okay, you have this guarantee here. Let me just rewrite it in a different way as the minimum over alpha of this quantity divided by alpha plus alpha. Again, alpha is not in the algorithm. It's just a way to rewrite the same thing. Let me compare it with what you get when in gradient descent, you use a learning rate alpha divided by square root of t. You get exactly the same convergence rate, but with an important difference. Alpha here, it's a parameter. You have to find it. Otherwise, this thing can be arbitrarily slow. Here, alpha is not a parameter, but somehow the algorithm will give you a guarantee as if you were able to choose the optimal alpha. There is a price that you pay for it. It's this logarithmic term here that, by the way, can also be reduced to logarithmic in x star minus x0, and you remove the dependency on time here, so that asymptotically, this is still 1 over square root of t. And so you have an algorithm that gives you the same convergence of an optimally tuned gradient descent without having anything to tune. You see here, there is nothing to tune. There are no learning rates, no parameters of any sort to use. So how does this work? And practically, you're basically using Krzyzewski-Trofimov. So in the first round, Krzyzewski-Trofimov tells you bet zero money because there is no bust. Then you observe the first gradient. The first gradient is a -1, so the coin is a +1. So in the next round, Krzyzewski-Trofimov tells you bet 50 cents. 50 cents means query the gradient in 0.5. You query the gradient here, is still exactly the same as before. And so Krzyzewski-Trofimov will tell you to bet more and more money, and you will keep winning money. And not only that, you know, because we proved it, that the wealth will increase exponentially. So this means that the algorithm will move exponentially fast from the initial point to the area of the optimum. Once you are here, at a certain moment, the algorithm will jump on the other side. Remember, gradients are coins. So once you are here, you observe a coin of the other side. You lost your bet. Given that you lost your bet, the wealth will decrease a lot. Wealth is equal to the point that you query. The algorithm will automatically backtrack. And then the average will converge, and basically here at a certain moment, the algorithm will jump back and forth around the minimum. So what the algorithm is doing, it's sort of the intuitive thing. When you are far from the optimum, take large jumps. Where you're close to the optimum, take very small jumps. But everything is done automatically. I never designed this behavior. It's given by the fact that Krzyzewski-Trofimov is optimal, and the optimization algorithm that I got is optimal. Now, just a couple of slides to convince you that this is not only theory, this actually works. This, I think, is the best way to convince you that this works. I designed a lot of different variations of this idea. One of them is called COCOB, and it was designed for deep learning. I put the software there on TensorFlow. Some random person downloaded and used it to win a Kaggle competition. And he won actually a lot of money with this. And this is, I think, the strongest way that I have to convince you that the algorithm actually works. If somebody took the code from internet, used it to win a real competition, means that, you know, there is something real in the algorithm. However, let me show you some sort of toy examples. These are just regression datasets. And what I plot here is that you just run stochastic gradient descent, one pass over the dataset, and then you look at the test loss. And I compare stochastic gradient descent, AdaGrad, that it's one of the algorithms that people like to claim that it's adaptive, but it's not completely adaptive. and pistol, that is yet another of these algorithms that I designed that are based on betting strategies. So what I'm plotting here is test loss compared to the initial learning rate, what I called alpha in that slide. So you have that there is an optimal initial learning rate that you have to use. For example, for SGD here, it's around 1. For undergrad here, it's around, I don't know, 5,000 probably. No, 500. But in order to find them, you just have to try all of them until you find the right one. In alternative, you can run my algorithm that is aligned because it doesn't have any parameter. And you get a performance that is close to the best tuned algorithm without doing anything. And this is sort of a very robust finding in multiple datasets. And in certain cases, I don't know if I have it, probably not. In certain cases, the performance of my algorithm is even better than a tuned undergrad. And we can prove that this thing is actually real. It's a real effect. This is, for example, one of the cases in which we have a slight advantage over a tuned version of undergrad.
Francesco, did you say that the pistol is the method that you were describing?
It's a variation of, I designed like tens of variations of this idea. Every time it's a slightly different betting algorithm, but every time it's exactly the same thing. The money that the strategy tells you to bet is X of T, the gradients are the coins. That's it. I'm just changing the betting strategy each time a little bit.
And so the reason why pistol is a line is because there is no such thing as eta.
Right, exactly. You just run it once.
I don't want to stop you because you're in the middle of this, but
Yes.
when you're finished with this part, I'm wondering how, because you had the animation of how the step sizes change and
Yes.
then it goes back.
Yes.
I just wanted to understand sort of after that what happens, because that picture
It will still go down again. It will still go down pretty fast again because you observed a lot of coins that were the same and only one on the other side. If you compute the Krzyzewski-Trofimov fraction, this is still saying bet on this gradient. And so you will still bet on that. You will still win money. And then you will smooth out the fact that you're jumping back and forth because you're taking the average of them. The average is actually important.
So basically it would go out that it would essentially go back to like 80% of the height that it was before and it start to do the smaller jumps and then getting larger again, and it will go back, and because the scale of the operation becomes smaller and smaller.
At a certain point, you basically
get
smaller and smaller. And
that sounds like there's a lot of iterations that is needed for things to
I mean, in this example, it might seem so, but in the end, no. I mean, empirically, this is I'm comparing algorithms doing exactly the same number of iterations here. SGD, undergrad, and pistol are doing exactly the same number of iterations.
As in, you basically cut it off after a certain numbers of runs to say that it has converged, or?
No, I just decide from the beginning, I will do just one pass over the entire data set, and that's it. This is stochastic gradient descent. So every time you take a sample, you calculate stochastic gradient. You do it for all the samples only once. There is a reason for that, because if you do only one pass, you can show that these optimize the test loss. If you do multiple pass, you're actually optimizing only the training error and not the test loss.
When you say one pass, what do you mean by, in terms of that animation that you showed in the
one pass? It
would have already converged to what it thinks as the optimized solution.
I don't know that. I don't check if I am converged or not. There is no way to check, by the way. There is no way to check.
So when we're looking at test loss, what is the loss that we're looking at? Is that the best that the algorithm can do, or this is?
It's just one pass over the training data. Okay, so basically you're doing a number of iterations that is equal to the number of training samples that you have. You stop and you look at the performance on the test set.
I guess the confusion is that this is not optimization performance. You're looking at classification or regression performance. I guess that's what you forgot to say.
No, this is a regression. This is absolute.
No, I'm saying as opposed to optimization performance. It's not.
No, it's actually, this is actually optimization because you're optimizing the test error directly, right? You have a distribution over simples that is unknown, and you're drawing simple from that distribution. So doing one pass over the training set is exactly minimizing the test error. So everything is exact. In this case offline, but there are no errors. I can explain this thing later. Okay. Okay, I just want to finish because sort of over time. So, I wanted to show you this in which you have a huge difference in what is the best performance of undergrad compared to pistol. And again, this is due to the fact that pistol somehow has undergrad. What undergrad is doing is that it has a different learning rate for each coordinate, but you still have to tune it. But you don't do it. You don't tune it for each single coordinate. You tune a single one for all the coordinates. And instead, pistol will give you sort of the best performance as if you tuned the learning rate for each single coordinate. That is something that it's unfeasible in reality. Okay, so let me conclude. So online betting basically can be solved using results from information theory. They're all there. I mean, and the funny thing is that you don't even find new results because people thought that everything is solved. It's basically finished. But there are a lot of problems that can be actually reduced to online betting. And so once you know these results, you can use them to do other stuff. So for example, we showed this very tight confidence interval with this numerical procedure. They are implicit in a certain sense, but they're still very tight. And the reduction was portfolio selections allow you to solve continuous coin betting that allows you to get uniform time concentration. Or you can do this thing that I call parameter free because there is no learning rate to tune. The entire thing is automatic. Online and stochastic optimization. And by the way, I show it for stochastic optimization, but actually works as it is even for online learning. So you don't have to assume that things are stochastic. They can be adversarial, and you prove a regret guarantee. And the reduction was continuous coin betting can be transformed into optimization without learning rates. Now, the thing is that there seems to be a missing link here. I don't know if it is there or not. So we show that gambling, betting is basically related to concentration. We also showed that optimization is related to gambling. And by the way, this is an equivalence here. We can also show that online optimization is equivalent to gambling. So maybe we can show some sort of connection between optimization and concentration. I still don't know exactly how this would look like, but this is something that is interesting for me to look at. Okay, so thanks for your attention and thanks to my collaborators. And sorry for going 5 minutes over time.
That's okay. We usually, we often go much longer.
Okay.
And we can still have a lengthy discussion.
Sure. Yes, of course.
Snow, are you still there?
Yes.
Yes.
Hello.
Do you want to turn off the recording and have a discussion? Is that
Yeah.
phase
Okay.
B?